Good morning, class. Today we're going to be looking at simple harmonic motion of springs and pendulums. Now, in our old textbook, this was chapter 10, but it is now chapter 13 in our new book, and we're only going to be looking at the first half of the chapter. Simple harmonic motion simply means motion with a periodic, which is periodic. That means repeats the same path over and over in the same time period. Mass on a spring. If the spring is hanging, you put a mass on it. It stretches it a little. You stretch it a little more and let go, and it oscillates up and down or goes through cycles. Oscillate is a synonym for the word cycle, which we'll talk about in a minute. Same for a pendulum. If you have a string with a bob on the end of it, you pull it back a little bit, let it go, and it will go through cycles, swinging back and forth. As long as we are talking about ideal springs and pendulums, their motion will continue forever because ideal springs and pendulums lose no kinetic energy to friction and air resistance and other things. So, simple harmonic motion. We're going to start today with springs, and to look at a spring, we have to remember that not all springs are made equal. Springs contain coils. The coils can be side by side, or they can be spaced out. This is actually a little spring from a pen. Most of you all probably recognize it as such. All right. The metal can be made of different metals. Some of them can be aluminum, they can be steel, they can be made of nickel, all sorts of different types of spring metals. Some of them, the wire that makes up the spring could be thick, it could be thin, it could have a narrow diameter like this one, or it could have a wide diameter. So not all springs are made equal, so they will exert different forces on masses. Okay. In fact, the force that that the spring exerts is called a restoring force, because the spring is always trying to restore itself to its original length. So if I push in on the ends of this spring, it's pushing back out, trying to restore itself. All right. And if I pull on it, it's pulling back, trying to restore itself to its original length. That's why in Hooke's law, which was is the principle discovered by Robert Hooke, the spring force is considered a negative value. We consider it a restoring force. When we exert a force on the spring pulls back with the same force, so we use the negative on it. It was Robert Hooke who first determined that the spring force is directly proportional to the amount of stretch that the spring is pulled through or compressed through. Now, understand, the stretch X, that is not a position in this case. I'm not crazy about the fact that they do it like this because we think of X as a position in kinematics. But in simple harmonic motion, X is a difference in length. It's the new length of the spring minus the original length. So a compression would have a negative value of stretch, and an actual pull or stretch of the spring would be a positive value. Okay? The K. The K is a physical constant based upon the properties of the spring itself. K is what we call the spring constant or stretch constant. Some books will call it spring constant, some will call it stretch constant, but it's the same thing. It's the property of the spring that tells you how many newtons of force it would take to stretch or compress the spring by 1 meter. And because springs are made differently, the K constant for each spring is different. Okay? In fact, if you were to graph, and I think I have it right here, if you were to graph the stretch of a spring versus the force that you exert to stretch it, The slope would be the K constant of the spring, because as you can see, this is a linear relationship. So if you solve for K, rise over run, the graph of F versus X is the slope of the graph. It's the K constant. Okay? The units for K would then be in newtons per meter. How many newtons of force it takes to stretch 1 meter. The stiffer the spring is, the larger the K value. All right? And an interesting little item, we're just going to mention this, is that if you have a spring of known length when it's unstrained, and unstrained means neither stretched nor compressed, if you cut that spring into half, each new half will not have the same K constant as the original spring. In fact, because you cut it into 2 equal pieces, each piece will have twice the K constant of the original spring. If you cut the spring into 3 equal pieces, each new piece will have 3 times the K constant of the original spring. If you cut the spring into 4 equal pieces, each new piece will have 4 times the original K constant. I think you guys can see where that's going. Another term we need to know about, and it's not actually typed in here, and I need to do that one of these days, but is the term elastic limit. The elastic limit of the spring is very important. You never want to exceed the elastic limit. The elastic limit is the point beyond which the spring cannot restore itself. In other words, you've deformed the wire to the point that it can't snap back to its original length. And the one thing you do not want to do with a spring is exceed its elastic limit. Now, let's see. If we look at a quick example, if you've got your calculators, oops, sorry about that, guys. Didn't mean to hit the tablet. If you've got your calculators right there, suppose you have a spring hung vertically and you put a 0.75 kilogram mass and attach it to the bottom. The unstrained length of the spring is 0.08 meters, but once you put the mass on the end and let it come to rest, you get 0.12 meters for the length of the spring. And we want to determine the K constant of the spring. Now, we know 3 things. We know the mass that we're going to place on the spring. We know the original length of the spring and the new length. Okay? Now, how can we determine? Well, what we have to understand is first, the stretch that the spring goes through is the difference in the old length and the new length. So that would be 0.04 meters. Secondly, we also have to understand that once it comes to rest, the spring force exerted on the mass would be the same as the weight of the mass because of equilibrium. So if we find the weight of the mass, we get 7.4 newtons, and we can use that as the spring force exerted to restore itself. So take the spring force, divide by the stretch, and you get that the K constant of that particular spring would have to be 185 newtons per meter. Okay, now, if a mass is hanging on a spring and it's in equilibrium, and then you pull it slightly so the spring is stretched, and then you release the mass, the weight of the mass, the gravity, and the restoring force of the spring will cause the mass to oscillate up and down in simple harmonic motion. Okay, so let's take a look at some definitions here. When the mass is going up and down on the spring, and oh, by the way, here at this point, I want to talk about one of the videos. In one of the videos, they are going to show you, actually in several of the videos, they're going to show you springs that are placed horizontally on a frictionless surface and attached to a mass. And I will let you view those videos to see how that works, but it's pretty much the same thing. They do show one short little video where they compare a vertically hung spring and a horizontally fastened spring. But these terms that we're going to look at are the same for both. The first is the term cycle or oscillation. One complete up and down motion, or back and forth if the spring is horizontal, is a cycle. That means if you have the mass stretched and then you let go and it begins to oscillate, it has to go through 2 pi radians to complete a cycle. So from where you let go, it has to go pi radians, stop, and then pi radians back to where it started. So that would be 2 pi radians, or 1 complete cycle. Period is the time it takes to complete a single cycle. So a period is the number of seconds to complete a cycle, one single cycle, and it is measured in seconds. On the other hand, if we reciprocate the period, we get the frequency, how often it goes up and down in 1 second. So frequency is the number of cycles in 1 second, the reciprocal of the period. We measure the number of cycles in a second as hertz. Now, the interesting thing about frequency and period are they are perfect reciprocals of each other. No proportionality constant is needed on either side to make the 2 sides equal. You just simply reciprocate one to get the other. Look at this example. It says, determine the frequency of a mass on a spring whose period is 1.8 seconds. So you simply take 1.8 seconds and reciprocate it. You can do that on your calculator fairly easily if you use the reciprocal button. Then you don't have to constantly stick in 1 divided by and then the period to get the frequency, or vice versa. The reciprocal button on your calculator, if you're not sure, looks like this on most calculators. It'll either say x to the negative 1, or it could say 1 over x. Either one, that is the reciprocal button, and you simply put in the number you want to reciprocate, hit that button, and it reciprocates it for you. Try it and see. Another term we need to be aware of is the term amplitude. Amplitude is a distance. It's the maximum displacement from equilibrium position. So if you have a mass on the end of a spring and it's hanging there at rest, it's in equilibrium. When you pull it down further to release and start oscillation, the distance you pull it down is the amplitude. In fact, when you start the oscillations, you are setting the amplitude. So that's its maximum displacement from the equilibrium position. So once you let it go, it's at the amplitude when you let it go. It accelerates up to the rest position. Then it decelerates past that the same distance above equilibrium. So you end up going with an amplitude that is above each part. So if this is the mass on the spring and this is equilibrium, okay, all right, at equilibrium, the spring force and the gravity balance. When you pull it down further, you've stretched the spring further. Okay? And when you let it go, that point is the amplitude. It will accelerate up to this point, at which time the acceleration will stop. One of the videos that you're going to see really explains this well because he can show it in motion, whereas I can't. All right, and then it will continue past that, compressing the spring until it gets to a point the same distance above equilibrium. I can't draw it very well, sorry guys. So that would be the amplitude also. It should be the same distance above and below. I just can't draw it very well right on the spur of the moment. So one of your videos, he does show you this in slow motion, and you can see it, and it's really very effective. So I highly suggest you watch the videos that I've put in your folders for you, because it makes so much more sense when you can see it actually in motion, and he has the points marked on the screen. It's really quite nice. The last characteristic, these are all characteristics of masses cycling on springs. You've got oscillation or cycle, period, frequency, amplitude, and the very last thing is velocity, and that's the speed at any point during the cycle. Understand, the speed of the mass on the spring is never constant when it's oscillating. It's constantly undergoing accelerations and decelerations. Even the acceleration value itself is changing because of the changing spring force. Remember, when the spring is different lengths, it exerts a different force. Now, the weight of the mass is always the same, but because the spring force is changing, then the net force is changing, and so is the acceleration. Now, two very important points you need to understand. Whenever a mass on a spring is oscillating and it's at the equilibrium position, because we know at rest the spring force and the weight balance, then anytime the mass goes through the equilibrium position, the net force becomes zero right there. And acceleration is also zero. Now, that doesn't mean it's not moving. It doesn't mean it stops. That means the acceleration is zero, and the velocity doesn't get any bigger than whatever it is. So, for example, if I release the mass down here, it accelerates up, but the spring force is getting smaller, so is the net force. The acceleration is getting smaller. So, when it reaches this point, the acceleration is zero, the velocity is as big as it's going to get, and then the spring begins to compress. The force gets even smaller. So we end up accelerating, okay, but in a downward direction. The acceleration points down. Since the mass is going up, it's slowing down. So it accelerates to the equilibrium position and decelerates to a stop at the top. And then we reverse the process. It accelerates towards the middle and decelerates towards the bottom. So you always get acceleration, deceleration, acceleration, deceleration. So we're always accelerating toward the equilibrium position and decelerating away from it. And again, the videos are much better at showing this than I can on paper. Please watch those videos. Right here, the velocity is going to be a maximum at equilibrium. It's going to be a minimum at the amplitudes, because that's where it changes direction. It has to stop to change direction. The acceleration, on the other hand, the maximums and minimums for the acceleration are just the reverse. The acceleration is a minimum at equilibrium, and it's a maximum where the velocity is changing direction. Just because the velocity is zero at these 2 points doesn't mean the acceleration is zero. So it's changing rapidly right here. It's not changing at all right here. So that is, the velocity is changing rapidly at amplitude and not at all at equilibrium. So the acceleration has a maximum at the amplitudes where the velocity is minimum, and it has a minimum or zero value at equilibrium where the velocity is at its maximum. So that's just the reverse for the max and mins for velocity and acceleration. All right, now I do have a picture of force. I'm going to let you guys copy that down. Okay, just like that. I'm just showing what the forces are doing so that you can see what the net force is in each situation and which way the acceleration would have to point. Remember, the net force and the acceleration always point in the same direction. So if we have a mass at equilibrium and we pull it down to the bottom and release, it will accelerate to this point because the upward force is greater than the downward force. But once it reaches equilibrium again, the two balance, acceleration stops at that instant, and you have your maximum velocity. But as it gets compressed going upward, we change directions. At least in this particular example I'm showing you, we change directions. Oh, the clock. Sorry, guys. All right, so now the greater the net force points down, so it begins to accelerate down. And then once it reaches equilibrium again, the net force is 0. Then the spring will begin to pull back up. So the spring force will, after this point, the spring force will start getting larger again, like over here. So the mass will slow down because the net force is now upward. So even though it's moving down, the acceleration will point up and you slow down. You can always pause the video here and copy what you need to copy. All right, now this next section I'm going to go through very rapidly. It usually confuses most people, but I'm going to try to just get to the meat of the matter. And the meat of the matter is that uniform circular motion is closely related to simple harmonic motion because both work in cycles. Both have cycles and are periodic. So, for example, let's say you have, let me explain the diagram here. What you have is a mass on a turntable of some radius, and the mass is going around and around on the turntable. You've got a bank of lights, and you shine it across the turntable. We're looking down on top, by the way. It shines across and shines a shadow of the mass on the wall. So as the mass goes around the circle on the wall, the shadow goes back and forth, very much like a mass on a spring. So we can look and see how uniform circular motion and simple harmonic motion are related to each other. Basically, we look at, for example, if we look at a position on the wall right here, okay, then when the object is right here, even though the radius is the amplitude when it's over here, its position right here is a component of that amplitude. So we can say its position on the wall would be the hypotenuse, the amplitude, times the cosine of whatever this angular displacement is. So amplitude times the cosine of the angle gives us the distance from the center that the shadow appears to be. All right. Those of you in calculus, you will recognize some of these formulas. So basically, the position on the wall at any time is going to be A cosine theta, where, if you'll remember, the angular displacement is omega times t. So all I've done is take omega times t and substituted it in for theta, because you do have an angular velocity here, okay? Now, the position is going to be a minimum right here, because that would be the center of the shadow's oscillation, like the equilibrium position for a mass on a spring. That would be at 90 degrees and again at 270. So the position is 0 at 90 degrees and 270 degrees, but it's going to be a maximum when the shadow is right out here at the 0 or 180 degree point. All right, because then the cosine of 180 or 0 is just 1, and 1 times A is A. So X is a maximum when it's at this amplitude or this amplitude. Okay? So right there, that's how they're related. In fact, you will see this on your formula sheet. So it's important that you understand this. Not so much important about the other two, but if you're in calculus, you will recognize that the derivative of the position gives you this. A omega sine omega t. If you want to find the velocity with respect to the angular motion of the object going in a circle, if you want to find the velocity of the shadow, you would use the derivative of this, which is a omega sine omega t. Don't worry about this too much, guys. Usually, if you ever see it, it's only going to show you this one on the exam. I don't think I've ever seen this one. And you can go through that and look if you want and see that yes, it does make sense if you have certain angles, positions for here, what would be the speed of the shadow on the ball at those locations, and it'll tell you the maximum and minimum that we can look at. Same for the acceleration. You just take another derivative of the velocity, you get this, but we're not going to worry about that, okay? This is really the most important one. That's the one you all need to focus on. I did make a nice little chart right here. If you do want to look at the chart, you can pause it and copy that down. It's just showing how where the maxes and mins come from for position, velocity, and acceleration, and what they would be equivalent to. All right. Now, one thing I would like to talk about is the omega, the angular velocity. Now, if you'll remember from our rotational motion, omega, which is delta theta over t, is radians per second. But if you'll remember, a radian really is just a meter divided by a meter. It's not really anything. It's just a way of measuring arc. So we could actually think of this as being 1 over seconds. Okay? But what is 1 over seconds? Oh, that's a measure of frequency because it's hertz. Okay? It's hertz. So a lot of times you will see angular velocity called angular frequency as well. So this would be like linear frequency. Or tangential frequency. This would be like angular frequency. Now, the only difference is that right here, a radian is 2 pi. So if we put the 2 pi, well, I don't want to put it in the units. So the delta theta would be 2 pi. So basically, the angular frequency is going to be 2 pi times the translational frequency. Okay, because a radian, you get 1 cycle, and that's 2 pi radians. So 1 cycle in 1 second, and you get 2 pi times the linear frequency. So that's kind of an interesting little thing. Now, I've got it written 2 ways here. Since frequency is also the reciprocal of period, you could also write it like this. All right, F is 1 over T, so stick in 1 over T for the F, and you get this. So this is 2 ways you can write the angular frequency. You can write it in terms of the period or the linear or translational frequency. Those are nice little relationships that can be used for substitutions to help you with stuff. It's kind of cool. All right, and there it is, angular frequency. All right, now here is an example. I'm going to show it to you right here. Oh, wait, no, I had to skip that example because it's not set up properly, and I didn't know it at the time, and I've never fixed it, so all right. Let's just hop on down right here. Okay, another relationship that you need to understand with angular frequency is how it's related to the K constant of a mass on a spring. And using Newton's second law, we can relate it. They do go through a proof, I think, in your book, but we don't really need to know that. That's not I've never seen anything about it on the exam. So basically, all we have to know is angular frequency is also equivalent to the square root of K over M. The spring constant divided by the mass that's placed on the spring. That's not the mass of the spring. That's the mass placed on the spring. Okay? So if we take that and substitute it back up here, we can find how I need some paper here. There's a spot. We can determine how to find the period of a mass on a spring because here's what I did. I took this, all right, and I did numerator denominator switch, right? And if you do that, then you get 2 pi over the angular frequency. But the angular frequency is the square root of K over M. So you would have a ratio in a denominator. Well, if you remember, when you have a ratio in a denominator, all you have to do is multiply by the reciprocal. So I did that. I just reciprocated the ratio, and I have 2 pi times 1 over omega. This is 1 over omega, okay? So you end up with this little ratio, formula. A lot of you from physics last year will recognize this as what we used for the period of a spring last year. 2 pi on the square root of M over K. And that's a handy dandy way. This is on your equation sheet for the exam too. That's a handy dandy way of finding the period for mass on a spring. Now, as you know, obviously you could take a stopwatch and time what the period of the cycles would be, and then you could also take M divided by K and find the period this way and see if they're the same. They should be if you measure carefully. Here's an example right here. I'll let you work on that yourself, and you can see if you have questions, you can always ask me about it. And then at the very last part of that question, we use the period formula for a spring. Let me put the S on the T right there, in order to find the period. So first we found the force acting on the spring, which would be the weight. The weight pulls down, the spring pulls back, but if it's in equilibrium, they're the same. You get let's see, you get the amplitude when it's compressed to a certain distance. You can find the K using Hooke's law. And then knowing the K, you can find the period of the spring in the shock absorber. Okay, we are going to